So you've probably seen rooms or at least pictures of them where, there's a lot of cables. Computer technology and digital technology is huge, and is a big part of our lives now. Understanding now, moving from electrostatics now into current, this is a huge deal where we're dealing with, charge moving through wires and analyzing that. And this is a little bit more practical than static electricity was, although in static electricity, there are a lot of practical applications too. But for our everyday lives, when we're dealing with cables and charge going through cables, it's a big deal. So when we're talking about current, we get back to Ben Franklin here, which I mentioned in the first unit, and this is the letter, this correspondence between him and Peter Collision, and I hope I said his name right. But yeah, you can read that real quick. Remember that Ben Franklin had a 50-50 shot, and being able to identify what's what in terms of charge and what was happening, and it was backwards. And so you can read that here, and then when you're ready to continue, you can hit play. All right. Okay, so current is defined as the flow of positive charge. And again, this is kind of reverse intuition because, we know it's actually electrons going through, but when we define current, defining it as the flow of positive charge. And yeah, it's how many coulombs per second pass through. So the, if we had a wire, and let's say we had charge in this wire, right? And we said, okay, this is the location we're paying attention to. And we look at how much Q, how much charge in coulombs passes through in a given amount of time. That's how much current we have. And so, it's, in a normal circuit, right? We think about it, the electrons are actually carrying the charge. That's the charge carrier, right? But if we define current, right? Current is the opposite direction. It's the flow of positive charge. So electrons move in random directions within a conductor like a gas container, right? So, once an electric field is established inside, we can have current flowing through. And so that's really what's required. We have to have that electric field. So we want to find in this one here, how many electrons per hour flow past the point in the circuit if it's 11.4 milliamps of current. And so, yeah, I think you should be able to figure that out. Why don't you go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so we know the current and we know the time. We're going to have 41.04 coulombs passing through in an hour. And we know the charge of one electron, so we can divide that out, and this is how many electrons it'll take. A lot of electrons to make that amount of charge, 2.56, 5 times 10 to the 20th electrons. So if the electrons are moving north, we want to find the direction of the current. The direction of the current would therefore be south. Okay, so let's say we have this wire, and we have an electric field established inside, and again, that's the only way that we're going to have current move, is if we have an electric field, have charge move. So we have an electric field inside, and we set that up right and have it to make the charge move. So here's our charges, and let's say that we set them an electric field, and the charges are going to be moving more or less in this direction. Now, they're going to have a certain velocity or certain speed called drift speed. And then they're also, in a period of time, we're going to be moving through. So if we consider that, right, we have a certain velocity times a period of time, that's going to be a certain length that it's going to cover. And so let's say in a given amount of time, only these ones that are highlighted are going to make it past this cross section of the area here, which is the circle at the far right. So only these particles are going to make it through in that period of time. And so drift speed is the speed at which the electrons move opposite to the direction of the electric field in a given amount of time. Remember, the field will actually be set up this way because electrons move opposite direction of the field. Because the field is defined as, what's going to happen to a positive point charge there. And so the field is set up from right to left. The particles are going to be moving from left to right. All right, so we want to estimate the drift speed in a wire that has a current of 1 amp. And so the wire has a radius of 2 millimeters, and the number of electrons per volume is 10 to the 28th electrons per meters cubed. So if you had a 1 meter by 1 meter by 1 meter, that's how many electrons you would have. So we're going to be able to use this information to figure out the drift speed, essentially the average speed of the electrons as they pass through. We have a certain cross-section of the area here. Every charge in there is Q, charge in an electron. And we know current is how much charge in a period of time, Q over T. And we have velocity times time, will be a certain length. So if we multiply that length times the area there, right, V times T would give us delta X, how far they go in a period of time. So, we would have length times area. And we know that's volume, right? Length times area would be volume. We have the area here. And then if we know the length of this, we multiply that. Volume is equal to pi r squared, which is the area times length or height or whatever. And so we can get the volume there. We know that how many electrons there are per meters cubed, so that'll help us out. So V times T times A, which is the velocity times time, and as the particles move across, times the cross-sectional area, that'll give us the volume. And so we'll have the volume in meters cubed, and then we're going to have the number of electrons per meters cubed, and then we're going to have the charge in coulombs, and that's going to give us Q, because the volume here is going to cancel out for this. We're going to have the number of electrons, so we'll number the electrons times the elementary charge E, and that will give us Q, how much Q actually passes by here in a certain amount of time. We could place that all in there. When we do that, our times will cancel out, and so the current is equal to the average speed, the drift speed, times the area, times the number of electrons per volume, and times the elementary charge. So we've got 1 amp in this situation, pi r squared. We've got the 10 to the 28th electrons per meters cubed, and the charge in an electron, and we should get an average drift speed of 4.97 times 10 to the negative 5th meters per second. So what you may be wondering is, this is actually very slow. And so the question I want to run by you is, why then, you turn on a switch, why does it take long time, not hardly any time at all for the lights to come on? And so, yeah, because you turn the switch on pretty much right away, right? So this is maybe helpful to visualize with, a water faucet, right? That water is all there, right? It's just when you open the faucet up, that water will flow. If your faucet breaks, there's nothing that's going to stop that water from keep going until you actually block that water, right? Same thing with the similar idea with electrical current, right? All of those electrons are ready to go. They're sitting in there, they're ready to go. When you close that switch, they're all going to start to move, even though they're moving slowly. And so, they'll move across.